everyone. We have been discussing the thermodynamics of polymer solutions in the last few lectures. So we have discussed the Flory-Huggins theory and used it to derive an expression for the Gibbs free energy change of mixing for a polymer solution. We also discussed the Flory-Huggins interaction parameter, what's its significance, how it depends on temperature. We have discussed the solubility parameter approach, which can be used to get a feel of the solubility of a polymer in a given solvent. So, although it might not provide very accurate results, it might be limited to only polymers and solvents which are non-polar, but still it is a useful method through which one can determine or get an idea of whether a certain polymer is soluble in a given solvent. So, we will continue our discussion of this topic of thermodynamics of polymer solutions, and in today's lecture we will focus on the phase behavior and especially the phase separation of polymer solutions. So, we will look at the phase diagrams, the concept of critical temperatures in these phase diagrams in the present lecture. We will also start our discussion on the thermodynamics of polymer blends towards the end of this lecture. So, specifically in the present lecture, we will first talk about the condition of equilibrium and that of stability of a polymer solution that is formed by mixing a polymer in a solvent. So, what is the condition for the solution to actually form, and even if it can form, whether that solution will remain stable or whether it will tend to separate into different phases. So, the conditions for these will look into these topics through graphical as well as mathematical approach. We will discuss the phase behavior of this polymer solutions using Flory-Huggins theory, and we will also talk about the phase separation behavior. We will also discuss what is called the critical temperature associated with the phase behavior of polymer solutions. So, specifically we will talk about two types of critical temperature, the lower critical solution temperature and the upper critical solution temperature. And as I mentioned, we will also briefly start our discussion of the thermodynamics of polymer blends towards the end of this lecture. So, when we talk about equilibrium, if we mix a polymer and a solvent to form a polymer solution, so the equilibrium condition for equilibrium is that the Gibbs energy change of mixing must be negative. So, the solution will form only when the Gibbs energy of the system actually goes down or decreases. So, which implies that the delta G of mixing must be negative. Now, that is fine if we mix a polymer and solvent, and if the Gibbs free energy of the mixture is lower than the sum of the Gibbs free energies of the individual components, then that will give a negative delta G of mixing, and that will satisfy the equilibrium condition that delta G should be less than 0. However, even if that condition is satisfied, there is no guarantee that the solution that has formed upon mixing of the two components, that solution will remain stable. So, if we mix two components, solvent and the polymer, and we form a solution, then if the solution that is formed can separate into two different phases, and that separation, if that separation can actually lead to further reduction of the Gibbs free energy of the system, then that phase separation actually will take place, and ultimately we will end up with a system having two distinct phases, one which will be rich in the polymer and the other which will be rich in the solvent. So, the delta G being less than 0, that is of course required for the solution to form, but even if that condition is satisfied, there is no guarantee that homogeneous solution that is formed, it will remain stable. So, some other conditions need to be looked upon, which will help us determine whether the solution that is formed will remain stable or whether it is unstable and it will phase separate into different phases. So, the condition for stability of a homogeneous energy solution is that if we construct a plot of the delta G of mixing against composition. So, for our case we will consider the volume fraction of the polymer in the solution as the measure of composition. So that we have been representing as phi 2. So phi 2 will be the measure of our composition. So if we plot delta G of mixing against phi 2, so if that plot is convex downwards throughout, then we can say that throughout the composition range the solution, homogeneous solution that is formed, is stable. However, if that is not the case, then there will be regions in which the stability condition will be violated, and the solution, homogeneous solution, will actually separate into different phases so as to further reduce its Gibbs free energy. As I just discussed, the stability condition is that the delta G of mixing curve should be locally convex downwards. So if we look at a typical delta G of mixing curve of this type plotted with respect to phi 2, then the locally convex downwards, which implies local stability, is will look something like this. So here we see that throughout the composition range, that is from phi 2 equal to 0 to phi 2 equal to 1, throughout this range the plot is actually convex downwards. So what this means is that throughout this composition range, the solution that is formed will be stable. So now that is a graphical condition for stability. Equivalently, we can also state the condition for stability in mathematical form. That condition of local stability is that the second derivative of this delta G of mixing with respect to phi 2, that should be greater than 0. So this is a necessary condition for stability. If this condition is satisfied, only then stability can be expected. And if this condition is violated, if delta G, the second derivative of delta G of mixing is less than 0, then the solution that is formed will be actually unstable. So we will discuss these things in more detail further down this lecture. So let us consider a solution that is formed at this composition phi 2 naught. This is approximately 0.4, so the solution contains around 0.4 volume fraction of polymer, and remaining will be solvent. So corresponding to this composition, if we form a solution, the delta G of mixing is given by the delta Gm naught here. And let's, for the sake of argument, let's see what happens if this solution, homogeneous solution that has formed at this condition, if that separates into two different phases. So whether that separation into two different phases, whether that will lead to a further reduction of delta G of mixing or not, let's find out. So let's say that this at this composition, the solution that has formed, that phase separates into two phases, one having composition corresponding to that point, and the other having composition corresponding to this point. And let's say the corresponding compositions are phi 2 alpha and phi 2 beta, and the two phases that are formed are the alpha phase and the beta phase. So now if we consider these two phases, then the delta G of mixing with respect again to the pure components, that is a pure solvent and pure polymer, the delta G of mixing for this system, which consists of two phases, will be given by the delta Gm alpha beta, that's shown here. And we see that this delta Gm alpha beta is clearly higher than the delta Gm naught, which we got if the solution remained homogeneous and did not phase separate. So since this delta Gm naught is less than the delta Gm alpha beta, and that will be true for any point on the curve that we have here. So whether we choose this point here, or whether we choose this point or any other point, that point will always have give a lower give delta G of mixing compared to a phase separated system containing two distinct phases. So for all cases, what this implies is that the homogeneous solution will be stable, and it will not phase separate into two distinct phases. So no phase separation will take place. So if we now consider a curve of delta Gm, which actually is not convex downwards throughout, but actually shows a concave region in the middle part, then things become a bit more interesting. By drawing what's called a common tangent to this curve, which shows two minima, we can identify 2 points which let's call as phi 2 b prime and phi 2 b double prime. These 2 points are what's called the binodal points, and these 2 points demarcate regions of stability for a system of this that shows this kind of a behavior. So if we have a solution that forms at that composition, it will be stable, and similarly any solution that forms above phi 2 b double prime, above that composition, that will also be stable. And this method by which we have identified the 2 points phi 2 b prime and phi 2 b double prime, that method is called the common tangent rule. So basically what we have done is drawn a common tangent to the two regions of the curve that show minima, and this common tangent construction gives us the binodal points. So we see that in this particular case the curve is asymmetric, and the two minima basically have different depths. So for cases with the curve, this delta GM plot or curve is asymmetric, for such cases the binodal points will not actually entirely coincide with the points of the minimum in those regions. So the phi 2 b prime here, it will not coincide with the minimum here. Similarly the phi 2 b double prime, that will also need not coincide with the minimum here. If we consider the region between phi 2 b prime and phi 2 b double prime, so that region is demarcated by this range, and that region is the region in which phase separation will take place. So this region between where the composition is greater than phi 2 b prime and less than phi 2 b double prime, that is the region between the binodal points, that part is referred to as the miscibility gap, because that is the region where the polymer solution will not be remain homogeneous, and it will not be miscible, and it will have a tendency to separate into two different phases. Now let us again look at a homogeneous solution having a certain composition in the region of miscibility gap, and let us see what happens in this case. So let us say this phi 2 naught is that composition that we again identified, but we see that this composition lies in a region where the solution need not be stable, so it lies in the miscibility gap. So corresponding to this composition phi 2 naught, the delta GM naught can be obtained like this, and if instead of having this homogeneous solution here, if this solution separates into two phases corresponding to the two binodal compositions, then the Gibbs free energy change of mixing delta GM alpha beta. So again let us call the two phases that have formed as alpha and beta phase. So the Gibbs free energy change of mixing will be given by this point here. So we clearly see in this case that the Gibbs free energy change of mixing actually has reduced when phase separation takes place. What we can infer from here is that if we have try to form a homogeneous solution having a composition phi 2 naught in this case, then that homogeneous solution will tend to separate into two different phases so as to further minimize its Gibbs free energy, and the composition of the two phases will correspond to the two binodal points that we have identified using the common tangent rule. It is important to note that separation into phases having the binodal composition, that will give the minimum possible Gibbs free energy, and that is why that separation is thermodynamically favored and it happens. We can also consider any other point in this miscibility gap region, some at let us say some other phi 2 naught, and for this case also we can identify the delta GM naught if a solution were homogeneous, and if instead if it phase separates into two phases having the binodal compositions. So if it again phase separates into solution having these two compositions, then the corresponding delta GM alpha beta again can be identified like this, and we see that again the delta GM alpha beta is less than the delta GM corresponding to the pure homogeneous solution. So again the phase separation will be favored because it reduces the Gibbs free energy change of mixing. So for it, what one can see is that for any composition in the miscibility gap region, which is in this range, so for any phi lying in this range between the binodal points, it will always so happen that the phase separation will be thermodynamically favored, because the corresponding delta G of mixing will get reduced upon separation into phases corresponding to the binodal compositions phi 2 b prime and phi 2 b double prime. So, so in the miscibility gap, the phase separation will always be favored thermodynamically. Next, let us just schematically try to represent what we have been discussing thus far. So, let us say that this box here, this contains the pure solvent and its Gibbs free energy, let us say, is G1, and if we add polymer to this solvent having Gibbs free energy G2, then we will end up with a solution where the polymer will be dissolved in the solvent, and let us say the Gibbs free energy of this system is G12, and the volume fraction of the polymer, let us say, is phi 2 naught for this case. So, this case represents a homogeneous solution that has formed. So, now again, depending on what this composition is, whether this lies in the miscibility gap or whether it lies in the stable region, that will decide whether this homogeneous solution is stable or whether it will prefer to separate into two different phases. So, the delta G of mixing, of course, is given by G12 minus G1 plus G2, and that should be less than 0 for the solution to form at all. Now, if this phase separation of this homogeneous solution at this composition, if that phase separation takes place into an alpha phase and a beta phase having compositions phi 2 alpha and phi 2 beta respectively, so that phase separation will occur if the delta G of mixing corresponding to the formation of these two phases is lower than the delta G of mixing corresponding to the homogeneous solution that we have. Ultimately, whether the solution that has formed is stable or not, that will always be dictated by whether the solution formed can further reduce the Gibbs free energy of mixing by separating into two different phases. And we notice that the phase separation that takes place here, the alpha phase and the beta phase, so one phase will be rich in the solvent, the other phase will be rich in the polymer, and the overall volume fraction phi 2 naught in the homogeneous solution, that can be that will be equal to the volume fraction of an alpha phase that has formed multiplied by the volume fraction of polymer in that alpha phase plus the volume fraction of the beta phase that has formed, which is F beta, times the volume fraction of polymer in that beta phase. So, if we look at again at delta G of mixing versus phi 2 curve, which shows two convex regions along with a concave kind of region in the middle, then using, as just discussed, using the common tangent rule, we can construct this dashed red line as a common tangent to the two regions, and that common tangent can be used to identify the binodal compositions phi 2 b prime and phi 2 b double prime. So, now in the two regions denoted by volume fraction below phi 2 b prime or volume fraction above phi 2 b double prime. So, in these two regions which are shown as shaded in green here, the solution will be stable, and this second derivative of Gibbs free energy will be greater than 0, which is the necessary condition. So, it has to be satisfied. So, the solution will be stable, because if a solution forms in these composition ranges, then no kind of phase separation will further reduce its Gibbs free energy. If we consider now a couple of other points on this graph. So, let us consider 2 points phi 2 prime s and phi 2 prime double s, which are shown here. So, these 2 points have been identified as the points at which the second derivative of the delta G of mixing is 0. Okay. So, the 2 points in this curve where this del square delta gm del phi 2 square is 0, those 2 points are called the spinodal points, and they are represented as phi 2 prime s and phi 2 s double prime. So these spinodal points basically demarcate the region where the second derivative is positive and where the second derivative is negative. So so if we now consider the range shown here, also shown as a shaded region in the graph, as well as the range here, which again is shown as a shaded region. So these two compositions correspond to those between the binodal composition and the spinodal compositions. So if we consider these ranges, the solution, if it forms, we have a solution that forms with a composition lying in these ranges, then the solution is said to be metastable. Okay. So these spinodal points basically demarcate the regions up to which the solution will be metastable. And if we go to composition range that lies between the two spinodal points, so if the composition is between phi 2 s prime and phi 2 s double prime, then in that case the solution, if the solution forms having a composition in this range, then the solution will be unstable, and of course the second derivative of Gibbs free energy is less than 0, so it will necessarily be unstable. So now let us just briefly discuss what is the difference between the metastable region and the unstable region. So in the metastable region as well as the unstable region, thermodynamically the favorable state will be the phase separated state, where the solution separates into two phases having the two binodal compositions, so that it can further reduce its Gibbs free energy. However, in the metastable region, for this phase separation to occur, which is thermodynamically favorable, for this phase separation to occur, certain kind of barrier needs to be crossed. So in the metastable region, the phase separation will typically take place through a mechanism called nucleation and growth. For the nuclei of a critical size to form, which can further grow and finally lead to phase separation, certain kind of activation barrier will need to be crossed. So metastable regions, solution actually in the metastable region, although thermodynamically speaking it should always phase separate, it can stay in that region provided that the activation barrier for this formation of a nuclei of critical size is not overcome. So that is a metastable region. Now in the unstable region, which lies between the two spinodal points, in that region the phase separation will actually be completely spontaneous. So even the tiniest fluctuation in, let us say, composition will induce phase separation. So any solution that forms in the unstable region will spontaneously phase separate into two different phases corresponding to the binodal compositions and reduce its Gibbs free energy. This kind of a phase separation which takes place in the unstable region, that is region lying between the two spinodal compositions, this type of phase separation is referred to as spinodal decomposition. So again, to distinguish between the two, spinodal decomposition takes place in the unstable region, and it is induced by the tiniest of fluctuations in the system, whereas the nucleation and growth mechanism for phase separation, that takes place in the metastable region, and for the nucleation to start and progress, a certain barrier needs to be crossed for a nuclei of a critical size to form, which can then grow and lead to phase separation. Next, now look at the effect of temperature on the miscibility behavior of polymer solution. So here what we have done is shown a plot of delta G of mixing versus phi 2 at several different temperatures. So we see that for this particular case, as the temperature is being increased from 250 Kelvin onwards, we see that the delta G of mixing graph progressively becomes more and more negative. So what that suggests is that the miscibility of the polymer in the solvent is increasing, and if we go to high enough temperature, which is 350 K in this case, then the miscibility gap basically completely disappears, and we have a solution which will be completely homogeneous throughout the composition range. So, if we look at the lowest temperature in this graph, because that the one at 250 Kelvin. So, we see that let us say the binodal compositions are somewhere here. If we go up in temperature to 260 Kelvin, the binodal compositions are shifting a bit, and further at higher compositions or higher temperatures, the binodal composition will further shift. So, what we see is that as the temperature is being raised, in this case the miscibility gap actually keeps decreasing and at high enough temperature the system becomes miscible over the entire composition range. In this particular case, increasing temperatures are actually increasing miscibility. So, change in temperature always leads to change in miscibility behavior, but it need not be that increasing temperature always increases miscibility. There can be cases where increasing temperature can decrease miscibility, but for the particular example that we are considering here, it is clear that as the temperature is being increased, the composition over which the solution will be stable, that composition range keeps on increasing. So, now from the Gibbs free energy versus phi 2 curve drawn at different temperatures, we can actually use information from this curve to construct what is called a phase diagram of temperature versus volume fraction. So, this T versus phi 2 phase diagram, this we can construct if we have the Gibbs free energy change of mixing curves as a function of phi 2 at different temperatures. To construct a curve on the right hand side, this curve, if we want to construct this, what we need to do is identify first all the binodal points on the Gibbs free energy curve. So, if we let us say have the binodal points here and here at a certain temperature, then at that particular temperature on the right hand side curve, we can mark 2 points corresponding to the binodal compositions phi 2 b prime and phi 2 b double prime. Similarly, at a higher temperature, the binodal points will shift. So, let us say the binodal points are here now. So, again at that higher temperature, we can again mark the 2 binodal points. So, in this way, if we keep going up in temperature and identifying the binodal points from the Gibbs free energy curve and plotting those points on this T versus phi 2 curve, then we will get this the solid black curve that is shown on the right hand side, and that curve basically is referred to the binodal curve. So, if we look at this T versus phi 2 curve on the phase diagram on the right hand side in more detail, we can identify two regions in this phase diagram. The region lying inside this binodal curve. So, the binodal curve we just discussed is constructed by identifying the binodal points from the delta G versus phi 2 plot, and this is shown as the solid black line here. So, binodal curve basically demarcates the single phase region and the two phase region. So, if we are at temperature and composition which lie outside the binodal curve. So, if we are at this point, then if the mixing takes place at that composition and at that temperature. So, this temperature, let us say, and some composition here, if mixing is taking place at that condition, then a single homogeneous phase will form and it will be stable. However, in the two phase region that we have here, again if we try to form a mixture at this point, let us say, which corresponds to some volume fraction, let us say around 0.4 and some temperature here. So, in this at this point, if the mixture or solution is formed, it will prefer to phase separate into two phases, and so this region under the binodal curve is referred to as the two phase region, because the solutions formed at these conditions, at this temperature and composition under the binodal curve region, they will tend to phase separate into two phases. So, the black line, as I just mentioned, is a binodal curve. It is also referred to as the coexistence curve on this phase T versus phi 2 phase diagram. Now, if we look at this one more curve on this diagram, which is shown as the dashed blue line. that curve is referred to as a spinodal curve. And to construct this curve, again the this delta Gm versus phi 2, that plot can be used, and again at different temperatures the spinodal points where the second derivative becomes 0, those points can be identified, and at different temperatures those spinodal compositions can be plotted. And if we plot the spinodal compositions as a function of temperature, then we will get the spinodal curve, which is shown as the dashed blue line here. So, the region between the binodal and the spinodal curve, that is the metastable region that we previously discussed. So, so if we have solution that forms at a certain composition that corresponds to this point, so at a certain temperature and a certain composition which corresponds to this point, if we form a solution, that solution actually will be metastable. Thermodynamically it will prefer to phase separate because that will reduce its Gibbs free energy, but for phase separation to occur, a certain barrier for nucleation has to be crossed. So, if enough energy for crossing that barrier is not present, the phase separation might not spontaneously take place. So, that is the metastable region. And the region under the spinodal curve, so if we have this spinodal here, this region under the spinodal curve, that region denotes the unstable region, where if we form a solution in with composition temperature in that region, then it will always spontaneously phase separate by spinodal decomposition into two different phases. And finally, the maximum, so the curve that we have drawn here, it basically shows a maximum. So, the maximum point of both the binodal and the spinodal curve actually coincide, and that point where both the binodal and spinodal curves show maximum, that point is referred to as the critical point. So, again I would like to emphasize that this kind of a phase diagram, T versus phi 2 phase diagram, this kind of diagram is will be seen if the miscibility is actually increasing with increasing temperature. So, we see that as we go up in temperature, the miscibility is increasing, and above this critical point, if they are above this critical temperature, then for the entire composition range above this temperature, always a single phase will form. So, if we cross this critical temperature, then the system will become completely miscible over the entire composition range. So, miscibility is increasing with temperature, and above the critical temperature the system becomes completely miscible for all values of phi 2. So, that is valid only if miscibility is increasing with temperature. There are cases where miscibility actually can decrease with temperature as well. So, in that case the T versus phi 2 diagram actually will look inverted. So, we will discuss those the phase diagrams in a bit more detail after some time in this lecture. So, now we have talked about the graphical, or we have discussed the phase separation behavior from a graphical perspective or graphical approach. Next, let us try to explore the same concepts mathematically. So, for polymer solution, we have derived the expression for delta, the Gibbs free energy change of mixing using the Flory-Huggins theory. So, the corresponding Flory-Huggins equation relates the delta G of mixing with the volume fractions of the polymer and the solvent, and it contains a parameter called the chi parameter. We can also write this delta Gm in terms of the number of molecules capital N1 capital N2 instead of the number of moles small n1 small n2. So, both are equivalent, only difference is that instead of universal gas constant we now will have Boltzmann constant here. So, now using this Flory-Huggins equation, we like to mathematically explore the stability condition that we have discussed previously. To do that, let us try to first recast this Flory-Huggins equation, so that the delta Gm is expressed only as a function of phi 2, because we see that the stability condition is related to the second derivative of delta Gm with respect to phi 2. So, let us try to reformulate this equation, so that delta Gm is expressed only as a function of phi 2, and we eliminate other quantities like phi 1, n1 and n2. So, to do that, let us divide both sides by the total number of sites, so N1 plus Xn2. So if you recall the development of the Flory-Huggins equation, so there that the Flory-Huggins theory is a lattice based theory. So we assume the polymer and the solvent to be in the solution to be present on a lattice, and the total number of lattice sites or cells is equal to N1 plus Xn2, where N1 is the number of solvent molecules, N2 is the number of polymer molecules, and X is the number of segments in a single polymer molecule or a single polymer chain. So if we divide this delta Gm by the number of lattice cells, that will allow us to express the delta Gm in terms of phi 2 only. So on the right hand side we get this term, and if you recall, this term, this ratio is nothing but the definition of phi 1, the volume fraction of the solvent. Similarly, this term that we get, this actually can be related to phi 2, the volume fraction of the solute or the polymer, and again this is also phi 1, this one was also phi 1. This again, if you recall, this will come out to be phi 2 by X. So if we make these replacements, then the expression that we get is kBT times phi 1 ln phi 1 plus phi 2 by X ln phi 2 plus phi 1 phi 2 chi, and the delta Gm bar that we have shown here, that is just the delta Gm divided by N1 plus Xn2. So that's the basically the Gibbs energy change of mixing per unit lattice site. Phi 2 is again defined as Xn2 by N1 plus Xn2. So that is why this ratio we could write as phi 2 by X. So finally, this phi 1 and phi 2, their sum is 1, because we have binary solution of polymer and solvent. So phi 1 plus phi 2 will always be 1. So phi 1 we can write as 1 minus phi 2. If we substitute those this in these two places as well as here, then we get the expression for delta Gm bar. So delta Gm expressed on per unit lattice cell basis as shown here. So now we see that the delta Gm bar that we have, it's expressed only as a function of phi 2. So starting from this expression of delta Gm bar, now let's start differentiating this with respect to phi 2. So we know that the stability conditions are defined based on the second derivative of the delta Gm with respect to phi 2. So we'll successively differentiate the expression that we have obtained for delta Gm. We'll differentiate it 2 times, and the expression that we get for the second derivative, then we'll relate it to 0 and see what are the conditions that we come up with. The first derivative, if we see here, if we are differentiating this with respect to phi 2, we can differentiate this using the product rule. Similarly, this also can be differentiated using the product rule, and here this is we can re-express this simply as phi 2 minus phi 2 square. So that's what we have done here, and these two terms come from the differentiation of this term. These two come if we differentiate this. So upon further simplification, we see that this, of course, these two will cancel. Similarly, the phi 2 will cancel this phi 2 here. So upon further simplification, we will get a minus 1 here, and then this term 1 by X here, ln phi 2 by X, and the derivative of phi 2 minus phi 2 square, that will come out to be 1 minus 2 phi 2, and chi will remain. So in this discussion, what we are assuming is that the Flory-Huggins parameter is independent of composition. So we have discussed earlier that the Flory-Huggins parameter is a function of temperature. However, we have till now neglected the dependence of Flory-Huggins parameter on composition. So here also in the current discussion also we will assume that chi is independent of phi 2. However, it must be noted that there are systems and cases in which this chi parameter can actually be a function of the volume fraction of the or the composition of the polymer. But such systems we are neglecting in the current discussion. So next, if we again differentiate this one more time to get the second derivative which we want, so the derivative of this term, the second will be 0, 1 by x is also a constant with respect to phi 2, so differentiating this will also result in a 0 term. So from this we will get this term, and differentiation of this will get this term, and finally differentiating this will just result in a minus 2 times chi. So this is the expression for the second derivative of delta Gm that we have obtained, and based on the stability criteria that we have discussed earlier, what we can say is that if this value is less than 0, then the solution that has formed is definitely unstable, and it will spontaneously phase separate into two distinct phases corresponding to the binodal compositions. Now let us consider the case or the point where the second derivative is actually 0. So this condition defines the spinodal points as we have discussed earlier. So if we set the second derivative of Gibbs energy to 0, and we already have derived the expression for the second derivative of Gibbs energy to be this, then if we set this expression to as 0, then just rearranging the terms, we get that 1 over 1 minus phi 2 plus 1 over phi 2x, that will be equal to 2 times chi. And finally the chi s, where the subscript s denotes spinodal. So the subscript s here denotes the spinodal point. So the chi, or the Flory-Higgins parameter corresponding to the spinodal condition, the spinodal point, is expressed in terms of the volume fraction of the polymer and the number of segments using this expression here. So the applying the spinodal condition basically leads us to this expression. And finally, if we assume chi to be a function of t of this form, so if we say that chi is a plus b by t, which we have discussed earlier also, and it's a commonly assumed temperature dependence of the Flory-Higgins interaction parameter. So if we assume that, then here instead of chi s we can substitute that by a plus b by ts, where this subscript s again represents the temperature corresponding to the spinodal point. So if we do that, and if we again finally rearrange the terms, what we get is an expression for the spinodal temperature, or the temperature at spinodal point. Essentially this expression that we have, or the previous expression, this for Ts and chi s, these two represent what's called the spinodal curve. So if we consider different values of phi 2 in these expressions, that will give us different values of chi s or Ts. So using this equation, one can actually plot chi s versus phi 2, so as kind of a spinodal plot of Flory-Higgins parameter as a function of phi 2. Similarly, using this equation here, one can construct the spinodal curve which corresponds to the temperature versus phi 2 plot for the spinodal points. So using Flory-Higgins theory, these are the two equations for the spinodal curve that we obtain, one for the Flory-Higgins parameter and the other equivalently for the temperature. Now if you remember that the maximum of the spinodal curve coincides with the maximum of the binodal curve, and that corresponds to the critical point. The critical point basically can be mathematically identified by this condition, where if we plot chi s versus phi 2, then that will show a extremum, a maximum or a minimum. So essentially the derivative of chi s with respect to phi 2 will be 0 at that critical point, and let us say the composition at the critical point be represented by phi 2 c. So applying this condition for the critical point, what we get is first using the expression that we had derived for chi s in the just previously, we can differentiate that once with respect to phi 2 to get this expression, and we'll set that equal to 0 to get the critical point. Again we further simplify the expression and rearrange the terms, and upon rearrangement, what we get finally is that this ratio phi 2 c by 1 minus phi 2 c, that is comes out to equal to 1 over square root of x, and from this expression again by rearranging we can obtain an expression for phi 2 c in terms of x. We can take the square root of x up here, and we can take this up here. So we'll get this expression, and finally the expression for phi 2 c will be 1 over 1 plus square root of x. So that's the composition corresponding to the critical point that we obtain by setting the derivative of chi s with respect to phi 2 as 0. Equivalently, for Tc, the critical temperature again corresponds to the temperature which will be observed at the critical composition. So in the expression for the spinodal temperature that we have derived previously, if we substitute the critical composition in place of the compositions, and the critical composition expression we have already derived to with this, if we substitute these expressions here, then we will get an expression for the critical temperature. So substituting phi 2 c here as well as here, and then further simplifying, we can simplify the terms and we will get an expression of this kind, and then taking out this term as this and 1 plus square root of x as common, we will get this expression. And again simplifying that further, the final expression that we obtain is this. So Tc is equal to b over 1 plus square root of x square divided by 2x minus a. So a and b again are the parameters which relate the Floer-Huygens interaction parameter to temperature. Similarly, the critical Floer-Huygens parameter, critical Floer-Huygens interaction parameter, again that we can find by substituting the expression for phi 2 c in these two places. So the critical Floer-Huygens interaction parameter chi c we can obtain by substituting this expression in these two places, and upon substitution and simplification, what we get finally is that chi c is equal to half plus 1 over square root of x plus 1 over 2x. So what that this shows is that as the number of segments or the polymer chain become longer, the value of this critical Floer-Huygens interaction parameter will approach 0.5, and in the limit when x is infinity it will become 0.5, but for any real system x will be large number in hundreds of thousands, but will not be infinity. So typically chi c will be found to be in the range of 0.5 to 0.7. So if we now let's say use the expression that we have derived for considering the spinodal condition, so the Floer-Huygens interaction parameter corresponding to the spinodal condition, if we use that equation of chi s versus phi 2, and if we plot this, so on the x axis if we plot phi 2, and on the y axis if we plot chi s which is found using this equation here, then depending on the value of x or the number of polymer segments that we have, we observe a shift downwards and towards the left as the number of segments is being increased from 50 to 150. So if we consider the case of this 50 segments, then the critical composition mathematically we can calculate using the expression we have derived, and that comes out to be a point around 0.1239, and if we mark that on the graph, and if we also calculate the critical Floer-Huygens interaction parameter chi c using again the expression that we have derived, that comes out to be around 0.6514. So we see that it lies between 0.5 and 0.7, and we can mark it here. So this the critical points that we have calculated, that corresponds to minimum on this curve, and that's what the mathematical condition was which was used to derive these expressions. Similarly, if we increase the value of x and repeat the calculations, we see that phi 2 c actually goes down and the chi c also goes down. So the curve has shifted to downwards and towards the left, and at even higher values of x, which means longer polymer chains, then also phi 2 c further reduces, and similarly chi c also reduces further. So what we observe here is that as the polymer chain length is being increased, the critical composition progressively decreases, and also the value of the critical fluorine interaction parameter, that also decreases. Next, we can also construct spinodal curves of temperature versus phi 2 instead of chi versus phi 2. So for that we will use the temperature, the expression for temperature that we have derived corresponding to the spinodal condition, and again here at different values of phi 2 we can calculate the value of Ts and plot that to obtain the curves, and again if we change the value of x we will get different curves. So here we have shown three curves again at the same three values of x that we used previously at x equal to 50, 100 and 150, and for this specific case we have used a equal to 0.2, b equal to 125 just as an example. So b we see is positive in this case. So for these values the curves that we obtain are shown here in this plot, and we see that as we go from smaller to longer polymer chains, that is as we increase x from 50 to 150, the curves actually shift up and towards the left. So again if we perform calculations for x equal to 50, if we find out phi 2c, that will come out to be the same as what we did for the case of chi s versus phi 2. So we get 0.1239 as the critical composition, same as before, and if we find out Tc, that comes out to be 276.9 Kelvin. So that corresponds to the again the maximum point here, which is the critical point. So that's the Tc. Similarly, if we increase x to 100, then phi 2c decreases as previously, whereas Tc increases in this case to 308.64, and that corresponds to the critical point on this curve. And finally, for the longest polymer chains having x equal to 150, phi 2c will further decrease, and Tc will increase to 320, almost 325 Kelvin in this case, and that these 2 points will correspond to the maximum here, which is the critical point for this curve. So the kind of behavior that we see here, it's specific to the parameter b that we have chosen here. Okay, let's consider that critical temperature in a bit more detail. So we have assumed chi to depend on temperature using this kind of an expression. Now if b is greater than 0, this we have discussed briefly in a previous lecture as well, but now we will discuss these conditions in a bit more detail. So if b is greater than 0, what we can say is that chi will decrease as temperature increases. So if b is positive, if t is increasing, this second term will actually decrease and chi will also decrease. So for such a case, if we draw the phase diagram, it will look something like what's shown here, and it will show a maximum. So again the solid black line shows the binodal, and the dashed black line shows the spinodal compositions, or the binodal and spinodal curves, and the binodal marks the separation between the single phase region and the two phase region. So single phase region is the region outside the binodal, and two phase is inside the binodal, and we see that the top point, we have said that that's the critical point at the maximum, or the temperature corresponding to the top point is referred to as UCST, or the upper critical solution temperature. Okay, so this is a temperature such that above this temperature the solution will the single phase solution will be stable throughout the composition range. Next, if we consider a different case where b actually is decreasing with, or b is less than 0. Okay. So in this case, if b is less than 0, if we again assume this functionality, then chi will increase as temperature increases. So if so what we know is that a decrease in chi actually favors mixing, and an increase in chi works against miscibility. So if temperature is increasing, and if that is leading to increase in chi, then what that implies is that increase in temperature actually in this case lowers miscibility. That is in contrast to this case, So in the case on the left side, since chi is decreasing with temperature increase, so miscibility is actually increasing as temperature increases, and at high enough temperature the system becomes miscible over the entire composition range. But now let us get back to this condition. So here temperature increase leads to chi increase, so that leads to decrease in miscibility. So the typical temperature versus phi 2 phase diagram for this case will show a minimum, okay. And again the solid curve is the binodal, the dashed curve is the spinodal curve, and the two phase region is the region above the binodal, single phase region is the region below the binodal in this case. So if we are in a region, then if the solution forms in this region, it will spontaneously phase separate into two different phases, and if we are in the single phase region, then the solution that forms will be stable and remain homogeneous and single phase. So now in this case again the critical point can be identified as the point corresponding to the minimum of both the binodal and spinodal curves, and the temperature corresponding to this critical point, that is referred to as a lower critical solution temperature. So this temperature basically represents the temperature at above which immiscibility or phase separation can be seen. So below this lower critical solution temperature, no phase separation will occur, and the single phase will remain stable throughout the composition range. But if we go above this lower critical solution temperature, then depending on the composition that we are at, phase separation can occur. So these are two representative cases, one in which miscibility actually increases with increase in temperature, the other in which miscibility decreases with increase in temperature. There can also be cases where this B actually changes sign with temperature. So instead of B being in greater than 0 throughout or less than 0 throughout, if B changes sign with temperature, then that kind of behavior, that kind of change in sign will can reflect in the phase diagram as well. So so apart from the simple phase diagrams that we have discussed in the previous slide, some other kind of phase diagrams can also be seen in polymer solutions, where the system actually shows both LCST. So this is the LCST here, because it corresponds to the minimum of the binodal, and the same solution at a different temperature, it can show a UCST as well. So this more complex kind of phase behavior can be observed for cases where the parameter B actually changes sign with change in temperature. So we can have a case shown here where as temperature is increased, initially the miscibility is increasing, so that from let us say a two phase mixture, as temperature increase will become a single phase and miscibility will increase, but as temperature is further increased, the system can again become immiscible and separated in two phases. So such kind of more complex phase diagrams of course are also seen for different polymer systems. So in this particular case, the LCST is lying above the UCST. One can also have a case, so there are some few systems which show a phase behavior which is kind of a closed loop. Okay, so here the UCST is lying above the LCST, and this region is the two phase region inside this closed loop. So all sorts of different phase behaviors are possible, and we have tried to discuss some of the typical phase behavior and phase separation behavior observed in polymer solutions in our discussion today. Now that discussion basically completes our study of the thermodynamics of polymer solutions and its phase behavior, phase separation behavior, critical temperature. So all those things we have tried to discuss graphically as well as mathematically. Next we'll just briefly introduce the concept of thermodynamics of polymer blends in this lecture, and we'll carry forward that discussion in the next lecture as well. Polymer blends represents a uniform mixtures of two different polymers. So a polymer solution is where you have a polymer being dissolved in a solvent, whereas in a polymer blend both components are polymers. So you have two different polymers that are mixed together, and depending on their mutual interactions, they can either be immiscible, so that they do not mix. They can be partially miscible, or they can be in some cases perfectly miscible as well. So we have seen that the polymer solution thermodynamics can be described using the Flory-Huggins theory. So slight modification of Flory-Huggins theory actually can be used, or the slight modification of Flory-Huggins equation for polymer solution can be used for polymer blends. So the similar Flory-Huggins theory applies to polymer blends as well, and the equation that we get, that will also be similar to the Flory-Huggins equation. The only difference now is that since both the components are polymers, polymer 1 and 2, so we will need to define x1 as and x2 as the two quantities, x1 being the number of segments per molecule of polymer 1, and x2 being the number of segments of molecules for polymer 2. So now, based on this definition, the definition of the volume fractions phi 1 and phi 2, that also will change a bit. So phi 1 can be represented as x1 n1 by x1 n1 plus x2 n2, and phi 2 will be x2 n2 by x1 n1 plus x2 n2. So the definitions are similar to a polymer solution. Only difference is that this x1 appears now, because the first component is not a solvent, it is also a polymer, and it also contains multiple segments. So based on these considerations, the Flory-Huggins equation for the delta G of mixing for a polymer blend actually comes out to be what shown here. Any one of these two equations, both are equivalent. One is in terms of number of moles, the other in terms of number of molecules. So if you look carefully at this equation, the only difference is that so the first two terms are identical, the entropy terms are identical. The interaction term, the contact term, actually is slightly different because of the presence of this extra x1. So the number of polymer segments of polymer 1, that appears in the contact term here. So that's the only difference if we compare this to the Flory-Huggins equation for a polymer solution. Okay. So of course the equilibrium condition for thermodynamically will always be that the delta G of mixing, that should be less than 0. So that will be true for any system, it will be true for the mixing of a polymer blend as well. So the equation that we have shown here, that's called the Flory-Huggins equation for the Gibbs free energy change of mixing of polymer blend. It's very similar to the equation for a polymer solution, only this extra x1 term appears, and the chi, now the chi that appears here, that's called the Flory-Huggins polymer interaction parameter. So for a polymer solution, if we recall, the chi was the Flory-Huggins polymer solvent interaction parameter. For polymer blends, it's the polymer interaction parameter. And so now that we have an expression for delta Gm, and phi 1 and phi 2 as well for a polymer blend, if we again divide this delta Gm by the number of lattice cells. So now since we have a polymer blend, we have n1 molecules of polymer 1 and 2 molecules of polymer 2. Each molecule of polymer 1 contains x1 segments, each molecule of polymer 2 contains x2 segments. So the total number of cells is x1 n1 plus x2 n2. So if we divide this delta Gm by x1 n1 plus x2 n2, then if we again consider this equation here, we are basically dividing all the terms on the right hand side by x1 n1 plus x2 n2. So this first term, upon division by this quantity, this first term you will see will become phi 1 by x1. This term will become phi 2 by x2, this N2, and finally this, if we divide this x1 n1 by this quantity, then we'll end up with just a phi 1 term here, and upon doing that, the final expression that we get for delta gm, again expressed on per unit lattice cell basis. So the final expression that we have is again in terms of phi 2 only. So this is the expression, and if we compare it to the expression for polymer solution, then the only difference that one can see is that you get an x1 term here as well. Okay. So, but that extra x1 term actually has a significant impact on the phase behavior of polymer blends. So, one thing that can be inferred is that now these two terms, the two entropic terms, they will be quite small because both are divided by x1 and x2, which are large numbers, typically on the order of hundreds or thousands. So, these two terms will be small. So, for polymer blends, actually the contact or the interaction term involving the interaction parameter, that becomes quite important in describing the phase behavior. So, we'll conclude today's lecture here, and where we have discussed in detail the phase separation behavior of polymer solutions, both graphically as well as mathematically. We have used the Flory-Higgins equation and derived the stability conditions and derived equations for the spinodal curve and so on. And towards the end, we started our discussion of thermodynamics of polymer blends, where we saw that the Gibbs energy change of mixing, that expression is very similar to that for a polymer solution, except for the presence of one extra term. However, the Gibbs energy change of mixing in a polymer blend actually is influenced much more by the interaction or contact term, because the entropy term is quite small. So, the phase behavior is much more strongly influenced by the contact term involving the interaction parameter. And based on the expression of the Gibbs energy that we have derived for the polymer blend, what we will do in the next lecture is continue this discussion and try to derive the expressions for spinodal curve and try to draw some phase diagrams for polymer blends as well to better illustrate and understand the phase behavior. And after blends, we will also briefly discuss the phase behavior of copolymers, block copolymers especially. We will not go into too much detail because it is a bit of an advanced topic, but we will just briefly illustrate and outline the key features associated with phase behavior of block copolymers. Thank you.